Alright, so section 7.3 is on a topic that's probably new for most people, especially if you've taken Algebra 1 or Geometry. It's usually not covered in something called logarithms. We want to basically do four things. Number one is learn how to change back and forth between exponent form, which is something we've already seen, and then something called logarithm form, which is new. Go both directions, from logarithm to exponent or from exponent to logarithm. And then learn how to evaluate logarithms and also how to graph them. So those are the four tasks right here. And these are just a picture of a logarithm graph. You look at that blue graph right here. So that is this one right here. This blue graph is something we've already seen. It's the graph of y equals 2 to the x. The logarithm, basically the relationship between an exponent and a logarithm, is that they are inverses of each other. So a simple example, let's suppose we had this, we use that same one that we were just talking about, this equation right here. If you plug in x equals 4, you would get 16 for y. So the point 4 comma 16 is on that graph. The inverse is 16 comma 4. Inverse means you swap the x and the y. So that would be this one right here, x equals 2 to the y. And in just a sec we'll learn how to write that in terms of logarithm form. So those are just pictures. You can see they're reflected over that green line. The logarithm, again, is just basically the opposite of raising something to an exponent. Okay, so let's take a simple example. I'm not going to use 3 to the third because that might confuse people with the multiple instances of 3. Let's use this example. Let's say 4 to the third power is equal to 64. 4 times 4 times 4 equals 64. This right here is called exponential form. We're writing it as this number right here, which is the base. 4 is the base. 3 is the exponent. And 64 is the answer. Okay, here's how you'd write that in logarithm form. You would say the logarithm base 4. So that 4 right there is the same as this 4 right here. Okay, the logarithm base 4 of 64 is equal to 3. Okay, this right here is that same exponent on the left, that same exponent 3. So basically what this means is that you take this number, you raise it to this power, and you get that answer. It's another way of writing something in exponent form, basically. The log base 4 of 64, so the log base 4 of the answer is 64, is equal to the power that I raised 4 to, the power of 3. Okay, so that's another, essentially a way of writing writing powers. When you actually put this in equation form, it's usually the log base 4 of some input, I should say, some input x is equal to y. Whereas over here you're raising this to the x power and you're getting y as your answer. So that shows you how those kind of flipped around. Over here the x is the power, over here the x is the answer. So we're swapping the x and the y. So let's do a couple more of these. We want to write each of these in exponent form. So the log base 2 of 8 is equal to 3. That means take this base, raise it to that power, and get this answer. So that means 2 to the third power is equal to 8. That's how you write that in exponent form. Same thing right here. This number raised to this power equals that answer. So 4 to the negative 4 is equal to 1 over 256. And remember, when you're raising to a negative exponent, that's the same as flipping it and making it positive. So 4 to the fourth is 256. Alright, same thing right here. And when you're first getting used to this, you can kind of tell just based on how those numbers are supposed to relate. If you look at 4, 16, and 2, the only way that you get a true equation out of this is by taking this and raising it to the second power, and that would give you 16. So 4 to the second equals 16. That's how you would write that in exponent form. Right here it's this base raised to that power equals that answer. So 3 to the 6 equals 729. Again, what we're doing is taking those logarithms and we're writing them in exponential form. Okay, let's go the opposite way now. So now we have stuff that's in exponential form. Let's try to write it in logarithm form. So this is going to be the log, and the base is always the thing that you're raising to the power. So the base here is 15. So the 15 will go right there. 15 raised to what power? Raised to the third power equals what answer? Equals 3,375. So that right there is the logarithm form of that exponent equation. Same thing right here. Right here we're taking the log base 4. We're raising 4 to the 1/2 power. That's this 1/2 that goes right here. And it's going to equal this answer. It's going to equal 2. So it kind of travels in a circle. Base raised to power equals answer. Log base 4 of 2 equals 1/2. And remember, raising to the 1/2 power is like taking the square root. So it says the square root of 4 equals 2. Alright, a couple more here just to get the hang of it. So the log base 4 is the base, raised to the 3rd power is equal to this answer is equal to 64. There's that in logarithm form. This one should be the log base 125, because that's the base, raised to this power. So raised to the 1/3 power, and that is equal to 5. That's like taking the cube root. Remember, raising to the 1/3 power is like taking the cube root of 125. So let's double check those are right, and they are. Okay. Now we want to learn how to actually evaluate these. So here's how you can do that. We don't know what this equals yet, so let's say that that equals to some unknown, some x. And now basically what we want to do is change that into exponent form. So this base raised to that power equals that answer. So 16 to the x equals 4. We would like these to be the same base, and we can make them be the same base by changing 16 into 4 to the 2nd power, because that's what 16 equals, and we still have that x there, so we're going to put it there. Okay, now how can we simplify this? Well, you might have already recognized what 16 has to be raised to, but in case not, remember the exponent rules are to multiply those together. So 4 to the 2x equals, and this is like 4 to the 1st. So what must be true? If 4 to the 2x equals 4 to the 1st, that must mean that 2x is equal to that. 2x is equal to 1. And if we divide both sides by 2, we get x equals 1/2. 16 to the 1/2 equals 4, and that makes sense because raising to the 1/2 is like taking the square root. So that agrees with what we already know. Alright, let's evaluate each of these. So this is saying, again, we don't know what this equals. 3 to this unknown power equals 81. And we would like 81 to be a power of 3, and it is a power of 3. It's 3 to the 4th. So the idea is that we change them so that they have the same base. That means x has to be equal to this. It has to be equal to 4. Let's check, and it is. Alright, this one's a little bit trickier. So here we're going to take 1/2. Again, we don't know what this equals. 1/2 to this must equal 256. And again, we would like both of these to be the same power. And if you look at 1/2, that can be written as a power of 2, because that's like 1 over 2 to the 1st. And when you have something that's number on the bottom of a fraction, you can flip it to the top and make it negative. Remember, every time you flip basically a number that's on the bottom of a fraction, you flip it to the top, it becomes negative. It was on the top as negative, and you flip it, it would become positive. So this is the same as 2 to the -1. You're raising it to the x power. And then 256 also has to be a power of 2, and that turns out to be 2 to the 8th power. That's equivalent right there. We knew it had to be a power of 2 because otherwise there's no way to solve this without using a calculator. So that means if we multiply these together, we would get 2 to the -x, and that is equal to 2 to the 8th. That means -x must equal 8. And if we divide both sides by -1, we would get x is equal to -8 as our answer. And let's just check that, and it is -8. Okay, now we want to talk about how to graph these. So that it's always useful to see what the parent function of a logarithm looks like. That's basically the function that all other logarithm functions are based off of. And just a couple of things to point out. First of all, this base is never 1. That's what this means, because you can't, 1 to any power is equal to 1. So there's the restriction that you're not going to be raising 1 to any power. You're just going to get the same number every time. So the base can't be 1. Couple things to notice about these graphs. First of all, the domain could be anything positive, and the reason it can't be negative is because, remember, we're taking this number, we're raising it to a power, we're getting an answer. You can't raise something to an exponent and get a negative number. So for example, 2 to the 3rd equals 8. 2 to the negative third does not equal negative 8. It equals 1 over 2 to the third, which is 1 over 8. So no matter how negative the power you're raising it to, you're still going to get a positive number. That's why the domain is all positive real numbers. And the asymptote is, you can see it's this kind of line right here. Why does it not go to the left of that? And here's why. Y is equal to the log of some base to the x. Remember, we're taking this power and we're raising it to, so we're raising it to that, and we're getting this as our answer. So that means the asymptote, the x can't go to the left of 0 for the reasons we just said. You can't get a negative answer when you're raising something to a power. Okay, that is the parent function. It says continuous because obviously there's no breaks in the graph. The range could be anything. That's this arrow here goes down forever, and this very slowly rises up forever. It will take a long time to rise very high, but eventually will. And the intercept is right here. That means when you plug in 1 for x, what number to that equals 1? Well, any base raised to the 0 power would be equal to 1. So that 0.1 comma 0 will be on most logarithm graphs unless you start shifting it or changing it. Finally, the graph on the right side is basically when the base is a fraction, when it's in between 0 and 1. And in that case, you get this kind of downward sloping graph. And we'll see what that looks like in just a sec. All right, so graphing each function. A lot of these can be done in a calculator. We'll do a couple by hand just to show you what it looks like. So in this case, we want to pick convenient values for x that we could easily get y's for. And the easiest types of values to pick would be numbers that it's easy to raise 5, or sorry, you want to raise 5 to the y power to get x answers. And that means the numbers we want to pick for x are powers of 5. So I'm always going to put 1 in the middle, and you'll see why in just a sec. 5 is a power of 5, so is 25. And so is 1 over 5, or 1 over 5 to the 1. That's the same as 5 to the negative 1. So let's think about it. 5 to what power would equal 1? Well, that would have to be 5 to the 0 power would equal to 1. So that means the point 1 comma 0 is on our graph. So we'll plot that. 1, 0 would be right here. Okay, then 5 to what power? Again, we're taking this number and we're raising it to the y power in order to get x. So I already know that x in this example is 5. What power do I have to raise 5 to get 5? I have to raise it to the 1. So that means the point x equals 5, y equals 1 is on this graph. So that should put us right here. And then 5 to the what power is equal to 25. That would be 5 to the second. So the point 25 comma 2 is on that graph, and that's actually way, way out here, so I can't even really accurately fit it. You know, it's somewhere over there. Okay, then let's get 1 point in the negative direction. So when when 5 is raised to the negative 1 power, we get 1/5 as our x value. So that's our x, and our y would be negative 1. So 1/5 negative 1 puts us here. Remember, this is like an asymptote. It's never going to go into the negative x zones because we can't raise something to a power and get a negative answer. So that's roughly what the graph looks like. Okay, the second case would be, what if you're raising a fraction to a power? So let's make a table for that. We would get the log base 1/3 of x. That means we're taking 1/3, raising it to different powers, and getting x values. So actually in this case, it's slightly easier to start by filling in the y column. And I know that seems counterintuitive, but we're basically raising 1/3 to the y power in order to get x. So let's do that. Let's raise 1/3 to the negative 1, and then 1/3 to the 0, and then 1/3 to the first, and then 1/3 to the second, just to get how that looks. So raising 1/3 to the 0, that equals 1. Again, why are we filling in the y columns first? Because x is the answer that we're getting after we raise power. So that means the point y equals 0, x equals 1 is on this graph, just like it was on the other one. So we'll put that right here. 1/3 to the first equals 1. Remember, this number that we're raising, that's the y value. So we're going to have the point 1/3 comma 1 on this graph, which puts us 1/3, 1 puts us about right here. 1/3 to the second is 1/9. That means the x value is 1/9 and the y value is 2. So let's double check that. 1/9, 2 puts us about here, and you can see here this graph is kind of going the opposite direction as the other one because we're raising a fraction to a power. And then this direction, 1/3 to the -1, if we flip it and make it positive, that's 3 to the first, which is 3. So our x value here is 3 and our y value is -1. So 3, -1 puts us here, and then we're going to get this part of the graph going like that. Okay, so that is roughly what that's going to look like, essentially sloping the opposite direction as the other one. Alright, all of those rules that we've talked about in earlier chapters about transforming graphs still apply right here. So this number here tells you if you're going right or left. This number here tells you if you're going up or down. And remember the rule is add to x, go left, and add to y, go high. Add to x, go left, add to y, go high. This number in front tells us if we are going to be vertically stretching or shrinking. You vertically stretch if that number is greater than 1, which is what that says. You vertically compress it if it's a fraction. And then finally, if the a number is negative, that means you're going to be flipping across the x-axis. So it's similar to what we've done before. These problems in general are much harder to graph by hand, so I recommend using a graphing calculator for this. So I'll show you how to do that. First, let's graph the parent function. The parent function would just be the log base 10 of x. So that's the first thing we're going to graph. And in terms of where you find the logarithm, you go to math. Oops, let's get out of here for a sec. We go to y equals, and then we go to math, and you scroll all the way down to the a, log base, and we want a log base 10. And then I will input x just to see what that looks like. So there's the graph of the log base 10. But what we want to graph, let's remind ourselves, we want to graph 3 log base 10 of x plus 1. So the plus 1 is going to move it up 1, add to y, go high. The 3 is going to vertically stretch it. So let's verify that that's the picture that we get. Log base 10, and this is going to be x right here, and then we have to add plus 1. So this should move it up 1, should vertically stretch. You can see the red graph looks like it has been stretched out a little, and it has been bumped up 1. That's essentially what we would do. We could fill in a table of values, but it's more efficient to use a graphing calculator for these. And that's kind of what the picture looks like right there. Alright, this one right here, Desmos, that's another site you can use if you do not have a TI-83 or TI-84. This one here, the -3, remember add to x, go left, we're subtracting from x, so the -3 will move it right 3. And the 1/2 should vertically compress it because 1/2 is less than 1. If you take half of things, you're basically making them smaller or shrinking them. So let's graph both of these. We'll just change 1/4, by the way, is 0.25. So that's why I'm putting 0.25 there. And then we have 1/2 log base 1/4. So I'm going to put 0.5 there. That's the same as 1/2. And then we have math. We're going to go to log base. Our base is 0.25. You could write that as a fraction. It's probably easier just to write it as 0.25 x and then -3. And here's what our graph looks like. So you can see the red one has been shifted to the right 3, and it's been vertically compressed a little bit, which means horizontally it's been stretched out. If you want to get a slightly better picture, sometimes zoom fit gives you a better picture. That's about the same quality though, so it gives you a comparison of what those look like. The last example will be a word problem, and this is an example of when logarithms are used in real life. The Richter scale is based on logs. So for example, when an earthquake, if you have an earthquake of 8 and another earthquake of 9, the one that's 9, even though it's only one number higher, that means 10 to the first power higher. It's 10 times as intense. An earthquake of 10, you moved up 2 from 8 to 10. That means you're 10 to the 2 times as intense, or 100 times as intense. So the Richter scale is based on logarithms, powers of 10. And that's what this says right here. The increase in intensity between each number is 10 times. So an earthquake of 7 is 10 times more intense than one of 6. An earthquake of 8 would be 100 times more intense. Okay, here's the equation. Y equals 10 to the x minus 1. X is the Richter scale rating, and y is the intensity. It says use the information that they're giving us here on the right about the earthquake that hit Alaska on Good Friday in 1964. Prince William Sound, Alaska, was a 9.2. It's the biggest ever recorded in the United States. That means the intensity would be whatever this turns out to be, 9.2 minus 1, that's the same as 10 to the 8.2. So that's going to be a 1 with something like 8 zeros coming after it. So let's see what the actual intensity is. And I don't know if they give us the units here, but we could always look that up. So let's do this. Let's say 10 raised to the 8.2 power. This could be in megatons or something. Okay, so that's a huge number. That's 158,489,319. That's the intensity. And it says write an equation of the form y equals log base 10 of x plus c. That gives us the inverse of that. So remember, the inverse means that we're supposed to switch the x and the y. So that's what we will do. Here is our original function right here. If we switch the x and the y, x would go here and y would go here. Okay, now how do we change that? Well, we already practiced changing from log form to exponent form before. So this is going to be the logarithm base 10, 10 raised to this power, so 10 raised to the y minus 1 equals this answer right here, equals log base 10. And then we could finally solve that for y by adding 1 to both sides. So we get y equals the log base 10 of x plus 1. That right there would be the inverse. And if you graph this function and this function together, you would end up seeing those two being reflections of each other over the line y equals x. So that is section 7.3, Introduction to Logarithms.